I think this seemingly difficult question can be answered, at least partially, if we know if we recognize the main difference between ERIE and CMIP6. That's the ERIE has higher resolution. With higher resolution, we produce more small-scale processes, and with that, more fluctuations. So the idea is simple to say higher resolution will have a stronger fluctuation, and stronger fluctuation gives you stronger dissipation, and the dissipation as the internal restoring force will affect the response of the system. And the theoretical basis of that is the fluctuation-dissipation theorem. For those who don't know that, just believe me that this is a key theory in statistical mechanics. For a system in dynamical equilibrium, dissipation is always related to fluctuations, in particular to the variance of fluctuations. And for those who work with that, you may realize that fluctuation-dissipation theory is normally framed within the linear response framework. And in that framework, the dissipation is supposed to determine the response of the system. So today, I'm concentrating only on the first version of the fluctuation-dissipation theory without taking response into account, although I will briefly come to that at the very end, and concentrating on the relation between fluctuation and dissipation. Okay, this is my outline. I will give you briefly 2 examples, how that looks like, and then I give you some theoretical background for why we think that dissipation is related to fluctuations, and then demonstrate that using Lorenz 1963 model, and then show the dissipation in ERIE climates relative to CMIP6 climate, give you finally some implication and summary. So in the first example, this shows the decorrelation time of the 1000 annular mode. On the left is the annual mean situation, and to the right is the 1000 summer. And the violet plot shows the CMIP models, and the black and gray shows the ERA data. And in the middle are the ERIE simulations coupled and EMIP type of simulation. What you see is that CMIP6 tend to make SAM too persistent in the sense to have long decorrelation time, and this bias relative to ERA 5, and this bias is reduced in ERIE simulation. So stronger persistence means also less dissipation. So it seems to be that in ERIE we have stronger dissipation than in CMIP6. Another example is the ocean example, where we have we use icon ocean and drive it with exactly the same forcing, surface forcing, and run it at 3 different resolutions. I'm showing you here the leg 1 month autocorrelation function of zonal velocity, and you see that the correlation decreases with increasing resolution very clearly. So to say, there's stronger dissipation in simulation at higher resolution. So why does that come? We need to start with the model equations. A climate model is a forced dissipative system described by a high-dimensional state vector, that is this bold X. The evolution of that is determined by a set of equations given in the box. dx dt equals f of x, bold X. And the simple x is a component of the full state vector, and f of x is a function of the full state vector, including forcing and dissipation of x, of this component we consider. And the state vector, the dimension of that, is determined by the number of prognostic variable times number of grid points. So for CMIP6, we have order of 10 to 8 dimension, and for ERIE, we have 100 times more. And for the dissipation processes in the climate model, these are mainly eddy diffusivity and eddy viscosity. They are formulated in form of Laplacian or higher orders, and it is clear if we have a spectral model and dumping something like minus alpha x with alpha being positive. However, in grid point model, alpha depends on the particular spatial discretization we use. If we assume that the total dissipation of small x, this one component we can see a linear damping, this assumption, as we will see, has no effect for the conclusion we draw later on. Then the original system can be written in the other box given here below, and where we have this explicit damping minus alpha x that include all the dissipative process that damps component x, simple x. And then a function which is given below, h of x. This depends on the full state vector, including all components that interacts with the considered component. And this first part, I call it pre-existing dissipation. This is the dissipation that occurs in the equation of the considered component. So let's have a more closer look. We have already this pre-existing dissipation. These are the dissipation in the equation of the component we consider. But they are also an emergent dissipation. These are dissipation in the equations of x prime, a component or several components of the full state vector that interact with the considered component. And in those equations, they occur in the equation of x, and therefore they only unfold via forward integration, when you integrate system forward in time after interactions between x prime and x have taken place. And the total dissipation is the result from both, and therefore you can identify them only in the integrals of f of x, in the integrals of the differential forcing. I call it the integral forcing, G sub tau I. And tau is the integration time length. In that case, in the discrete case, integrated over tau time step. And I is the time from at which the integration starts. And this integral forcing, G tau, we assert it consists always, or take always the form, has a constant C tau, and then a dissipation, and this is now the total dissipation, including both the two types of dissipation I discussed before, in the sense that this d tau is always negative, and it provides maximum dissipation if d tau is -1. And then another term, which I call it fluctuating forcing of G. And this form of integral forcing is called integral fluctuation dissipation relation. And with that, you can show that the variance of the fluctuating forcing, sigma square sub f tau, divided or normalized by the variance of x, is directly related to the total dissipation. And given integral forcing G tau, you can make forecast tau time step ahead. And if during that time the maximum dissipation is reached, d tau equals -1, you will see that the initial state is completely eliminated. The solution will become independent to the initial state and therefore appear to be random. This three terms the total dissipation strings d tau and the constant c tau and the fluctuating forcing f tau can be obtained by regressing g tau against x. In that case, this d tau is simply the slope and the fluctuating forcing is the residual. Okay, but that's still not clear why it depends, does the dissipation depends on fluctuations. We investigate that by considering the autocorrelation function, tau. It can be shown that a rho at time step tau equals 1 plus d tau. And this can be decomposed into two parts. One exponential part, the first part on the right-hand side, that emerges from the pre-existing dissipation. We assume that it has a linear form, and therefore we have now this contribution in the exponential form. And the other part is a cross-covariance function between x and j, and normalized by the variance of x. And the j is given here below. You see it's a function of h. Remember, h is a part of the forcing of x, of the considered component, that does not contain any dissipation of x. But it's a function of the full state vector, and therefore it depends on other components of the system. And so the cross-covariance function, or the second term that contributes to the autocorrelation function, results from interaction between x and x prime that enters the h function. Consider the situation if there's no such interaction. In that case, there's also no emergent dissipation. Then the correlation function is solely, completely by the pre-existing dissipation. And it is not dependent on fluctuations. You see that because the correlation function is also normalized by covariance, normalized by the variance, and that cancels out, so that the correlation function is not dependent on variability. It's controlled by alpha, by the pre-existing damping completely. But in the other case, if there's no pre-existing damping alpha equals 0, we have to deal with only this covariance function between x and j. Then you'll see that the correlation function has to depend on fluctuation, more precisely on fluctuation of x prime that interact with x. Even though we have this normalization with divided by the variance of x, but now we have the variance of x prime that cannot be completely cancelled by this normalization. In particular, if x interacts with several x primes, then there's no way to really cancel that. And that's the place where fluctuation comes into. In that case, the dissipation in the component of x prime will also taking place, affects the dissipation of x, and that is seen in this cross-covariance function. And the correlation function were not determined by alpha only, by the pre-existing dissipation only, and the interaction between x and x prime can be either way, either forced or damped, and it will be a forcing when this cross-covariance function gamma is positive, and in that case you see that the correlation function will be larger than 1, and the dissipation factor d tau will be larger than 0. So that in that case it acts as a damping. However, that will not actually not happen that alpha equals 0. We're talking about forced dissipative system that is always there. Okay, so I have tried to explain why dissipation depends on fluctuation. This dependence comes through the cross component interaction, and through this interaction, the dissipation in other components will affect back to the component we consider. And this can be demonstrated easily through the Lorenz model. This is the Lorenz 1963 model with 3 components and with 3 equations. And in each of the equations, you have a linear damping, which is the first term on the right-hand side. And for the first component, x, we have the linear damping minus 10x. So the alpha is 10, and the part which does not contain any damping of x is this h of x, and this is equals minus 10y. And the total dissipation of x is determined not only by minus 10x in the equation of x, but also by minus y in the second equation, in the equation of y, because x interact with y, and actually also by minus 8/3 z in the third equation, because y interact with z. And how this looks like, I try to demonstrate here on the left. I show you the correlation in the at the lead time until 4. And on the right, the solid line is the total autocorrelation function. And the dashed line shows the part of the autocorrelation that comes from the pre-existing linear damping. And on the left, I show this second contribution to the total, to the correlation function related to the covariance between x and j. And you'll see that at this small time lag, they are all positive. And so that on the right, you'll see the solid line is always above the dashed line, the colors corresponding to different components. So that's, you'll see already the effect of this cross-component interactions that induce the emergent dissipation. And if you look at the longer time lags, you'll see that for the blue curve, that's the second component on the left, you'll see that this cross-component interaction actually becomes a damping. So it's become negative. And on the right, you'll see that the autocorrelation function, the solid blue line, is actually below the decorrelation function due to the pre-existing linear damping dashed line. The situation is opposite for the magenta line. The magenta line for the first component, this cross-component interaction acts always as the forcing. So this left magenta line is always positive, and on the right, you see the correlation function, solid line, magenta line, is above the dashed line, the damping that related to the linear damping explicit in X equation. So the situation can be different on longer times lags, but no matter how different, over sufficient long time, when all dissipations in different O3 equations become active and fully unfold, then the correlation function will vanish, goes to 0. Okay, what happens if we increase the fluctuation in the Lorenz system? Here in the Lorenz system, we keep everything the same, including the pre-existing linear damping. We only add white noise, N. And the variance of N is said to be proportional to the variance of the respective unperturbed differential forcing F. And that's what comes out. So what you see, what you see on the x-axis, that's the ratio of the standard deviation of the included noise to the standard deviation of the differential forcing unperturbed. So the stronger the ratio, the stronger the included variance noise. And On the y-axis, we look at first the dark color. That is the dark color indicates the total dissipation measured by d tau in the perturbed case with the sub-index n relative to the amplitude of unperturbed d tau. And you see that's negative, so that's we have dissipation, and -1 indicates there's no change. But what we see is that with increasing strength of fluctuation we put in through the noise, the dissipation increases. Although the pre-existing dissipation is the same, the linear damping is the same in the model. And so we see that given a tau, so this is a tau equals 8, the total dissipation strengthens with increasing noise. And this noise should be strong enough to make the change noticeable. We see that for the ratio, the first one, very weak noise, is only about 0.2 magnitude of the original forcing. The difference is hardly visible. The change is hardly visible. Only when you have strong enough fluctuation, then we see these effects clearly. And we see also that the dissipation is linked to the normalized variance of the variance of fluctuating forcing. These are shown by the light color. And again, 1 is ratio equal 1 indicates no change, and larger than 1 indicates change, increasing variance of the fluctuating forcing. So we see a clear relation between these two. And if you look at the whole covariance function, now I'm showing to the left, to the right is rho tau, that's the autocorrelation function. The dashed one is the one without the original, without any perturbation, without adding noise. And then we add the noise with increasing width of the line and lighter color, the noise intensity increases. So we see that the correlation function really decreases at all legs, at almost all legs, with increasing dissipation, increasing fluctuation. And the black solid line is the part of the autocorrelation that comes from the linear damping, and that is independent of fluctuation. That's always the same, no matter how you change the fluctuation. And this change of autocorrelation function comes from this covariance between cross-component interaction. Due to cross-component interaction shown in the left, you'll see that quantity decreases with increasing noise. That leads to the weakening of the autocorrelation function. So the autocorrelation function decays faster with stronger dissipation. So we see that this is also the case, actually, not only in theory, but also in this simple example that stronger fluctuation gives you stronger dissipation, although you didn't change the model. Now come to ERIE and CMIP6. And ERIE, we have 4 coupled models and 1 uncoupled run in AMIP type simulation. And the resolution is given there. And the CMIP6, we know that's of order of 100 kilometer resolution. And we consider here 20 historical runs. And we consider only geopotential height at 500 hectopascal daily value. And here, one thing to say is, you see, I take 30-year period, and there are different periods given, yeah. The thing is that these 30 years is truth and such, it is sufficiently long that statistics can convert dynamical equilibrium with stationary fluctuations, time average, like how you get the autocorrelation through time average or variance through time average. All time average will converge if the average, the numbers over which you average go to infinite. So we need a long record to ensure this conversion, to ensure a better estimate. On the other hand, the integral fluctuation dissipation relation holds only for system in dynamical equilibrium under constant forcing, and therefore we cannot take too long time period. And we think 30 years is short enough, also in historical runs, that the changes in external forcing can be neglected. So that's the reason why I chose 30 years. So what's the result? Oh, before we get result, we need to extend the fluctuation dissipation relation, which was formulated at each time step of the model, of your dynamical model, to a relation which holds for, in our case, daily averaged. And it can be shown that that is indeed the case. And the relation has a similar form as before. The overline with sub I indicates an average over all time steps within day I. And with that, we can estimate the total dissipation in our case, 500 millibar geopotential height within 1 day by either regressing the daily averaged integral forcing, and this is by definition the difference between the change of the geopotential height from another against the geopotential height. And this is, the other way will be then just calculate the autocorrelation, leg one autocorrelation, and get the dissipation from the autocorrelation. We choose the first way, and that means we do regression and get the d-tau. And this is what we get. So we have on the first row is for icon result, the second for EERIE ensemble mean, and the third, the bottom, is for CMIP6 average over the 20 members. And the first column shows the total dissipation strength d-tau, and in the middle we show normalized variance of fluctuating forcing, and to the right, a picture familiar with you shows the variance of geopotential height. And white indicate here in this case values around 0. So what we see is that the spatial structures are quite robust across the climates we consider, no matter whether it's EERIE climate or CMIP6 climate or icon climate. And we see also d-tau is negative everywhere. And we see also that d-tau is determined by the normalized variance of fluctuating forcing, not by the variance of the solution of the geopotential height. And you can see that in various cases, places. One is in the Southern Ocean, that the variance of geopotential height to the right has the maximum in the Southern Ocean in the Pacific sector. But for the variance, normalized variance of fluctuating forcing in the middle is in the Indian Ocean sector. And there are also other differences. And this comes because, the relation between these two variables comes from this integral fluctuation dissipation theory. And what I'm showing here in the below, in the x-axis is d-tau, in the y-axis is this normalized variance. And the relation is indicated by the curve. And the green dots are actually all values you see from icon, from the map, from the two maps at each grid points. And you see that they are completely determined by this relation, and therefore they align on this line. Okay, now we come to the point we want to make is whether resolution matters for dissipation. And how we show that is to consider the averaged total dissipation d tau averaged over ERIE ensemble relative to the magnitude of this quantity averaged over CMIP6 ensemble. Same, we consider the normalized variance of fluctuating forcing averaged over ERIE ensemble relative to those averaged over CMIP6. And that's what you get. So here, white color indicates values around 1, indicating no effect. And the green is we have negative values. In this case, for this dissipation, indicates stronger dissipation in ERIE relative to CMIP6. And the red, on the other hand, indicating the fluctuating forcing is stronger in ERIE relative to CMIP6. And the numbers you see, it's up to maximum in the northern polar region up to 30%. And but in most of the extratropical region around 10 to 20%. So we can conclude that the total dissipation in 500 millibar geopotential height within 1 day in ERIE climates is systematically different from that in CMIP6 climates. And this dissipation is about 10 to 20% stronger almost everywhere in ERIE than in CMIP6. Noticeable exception is the deep tropics. What happens in the deep tropics? Or why we have different behavior? To check that, we calculate this quantity at each grid point, and then consider the median of them in different latitudinal bands. We consider first extratropical bands in the southern hemisphere and in the northern hemisphere. And the x-axis is again the dissipation intensity. To the left is stronger dissipation, and the y-axis is fluctuation strength, increasing to the top. And the black dots are CMIP6. You'll see that in the extratropical region, the CMIP6 are located in the part have lower dissipation, weaker dissipation and lower weaker fluctuation. The colors are the ERIE models. They tend to located to having stronger dissipation and stronger fluctuation. And if we look at the head gem, we have the red star, that's the highest resolution, and then the green one, that's the median resolution, and the black star, that is the low resolution. And we see in both cases, the dissipation in the HH in the highest resolution is stronger than the gray star, the median resolution, and the median resolution dissipation is stronger than the low resolution dissipation. Same in the northern hemisphere. The situation, okay, so outside the tropics, outside the deep tropics, the dissipation tends to be stronger in ERIE simulations than in CMIP6. The situation is different in the tropics. In the tropics, if you forget about the icon, then you don't really see big difference. The colored symbols, the ERIE runs, are among the black symbols, the CMIP6 low resolution runs. And for the head gem, you see the gray star, the MM, has stronger dissipation than the red star, HH. And the black one is behind the orange symbol, and that has the lowest resolution. So in the inside the deep tropics, except icon is kind of an outlier. No difference, clear difference can be seen between CMIP and ERIE. And icon, as I have to say, in that differs from the other because it uses only very limited parameterizations. Probably the number of parameterizations used is the smallest compared to the other models. Possible reason for the similar behavior between EERIE and CMIP6 in the deep tropics. One is the dominance of parameterization. I mentioned that icon don't have too much parameterizations than the other. In particular, it does not have convection, does not have gravity wave drag. And the parameterization do not directly initiate interactions between grid points. And if they dominate, they can make the emergent dissipation whose existence onto the cross-component interaction, cross-grid point interaction. This will become insensitive, becomes weaker, insensitive to changes to fluctuation. That could be one explanation. The other is the numerical dissipation. And all the models are using either implicit or semi-implicit time stepping schemes because we want to make stable simulation using larger time steps. And therefore, you can do that with this type of scheme, but these schemes are generally always afflicted by some numerical dissipation. And the resolution-induced strengthening of fluctuation, if not strong enough, can be effectively damped by the numerical dissipation, leaving the emergent dissipation unchanged or even weaker. So if that is true, that means that increasing resolution does not increase too much fluctuation in the tropics, in the deep tropics, compared to in the exotropics. But this is something we need to further investigate. So to make some implications, I think you all know this diagram of Markov, and we have three climate change using different resolutions. And it turns out that the highest resolution, the green one, has the weakest GMST response. And suppose if the total dissipation really acts as internal restoring force, and if geopotential height capture much of the polar amplified warming signal, so to say the main signal is in the polar region where the dissipation really strengthens with increasing resolution in HEC-GEM, then the increasing resolution can weaken this warming signal by strengthening the total dissipation. This is one possibility, but you also know this plots by Markov. This is AMOC, and here we see different behavior. There's no clear indication what happens here. So I might say that total dissipation is only one of maybe many factors affecting the response. In particular for AMOC, the dissipation, total dissipation of velocity from which we calculate the AMOC might be not so effective in controlling the response of AMOC than other factors, such as buoyancy flux at surface. And therefore, that in that case, it doesn't really seem to show any systematic changes. Okay, summary. From theoretical perspective, total dissipation of a climate component or degree of freedom, X, is dominated not only by the pre-existing, that's dissipation in the equation of X, but also by emergent dissipation. Those are dissipation in the components which interacts with X. The emergent dissipation being not visible in the equation of X, they depends on fluctuations, and they only emerges through forward integration when the interactions have taken place. Therefore, the total dissipation cannot be diagnosed solely from the model equation. And it sits not in the differential form, differential forcing, it sits in the integral of the differential forcing G. So the integral forcing G. That's the theoretical side. And this we demonstrate using Lorenz model that increasing fluctuation strengthens total dissipation. Also, we don't change the damping term in the model. ERIE climate versus CMIP6 climate, we see a strengthening of dissipation in geopotential height within 1 day by about 10 to 20% in ERIE, except in the deep tropics. We see also ICON, which includes only the avoidable parameterizations. These are radiation, turbulence, and microphysics, reveals the strongest total dissipation. With that, I have a few references and thank you for your attention.